Friends, in this lecture, we'll discuss about CSMA slash CA. Okay, okay, CSMA slash CA. This is carrier sense multiple SS with collision avoidance CSMA slash CA, which was invented for wireless networks. Collisions are avoided through the use of CSMA/CA's three strategies. Collisions are avoided through the use of CSMA/CA's three strategies. One is interframe space, another is contention window, and one more is acknowledgement. Now we'll see what is interframe space IFS. First, collisions are avoided by deferring transmission even if the channel is found idle. The station does not send immediately when an idle channel is found. Rather waits for a period of time called interframe space or IFS. Even though the channel may appear idle when it is sensed, a distant station may have already started transmitting. Distant station signal has not yet reached this station. The IFS time allows the front of the transmitted signal by the distant station to reach this station. If the channel is still idle after waiting an IFS time, station can send, but it still needs to wait a time equal to the contention window. IFS variable can also be used to prioritize stations or frame types. For example, a station that is assigned a shorter IFS has a higher priority. Next, we'll see about contention window. Before going to contention window, we'll see the flow diagram of CSMA slash CA. So this is the flow diagram of CSMA slash CA. Okay. The legend is K number of attempts, TB back of time, IFS interframe space, RTS request to send, CTS clear to send. Then station has a frame to send if K equal to 0. If K equal to 0, then we have to check channel is free. If channel is free is true, then wait IFS. If channel free is false, go back for K. Again the process repetition. Then wait IFS. After waiting an IFS, there is contention window. Choose a random number r between 0 and 2 raised to k minus 1 and use the rth slot. Then send RTS. Set a timer. Set a timer. CTS received before timeout. CTS received before timeout. If it is true, wait IFS. If it is false, increment k by 1, k equal to 1. Then if k is less than limit, again we have to check. Then we'll proceed for wait IFS after send the frame. This is a transmission. Then set a timer. False. True. Acknowledgement received before timeout. Check it. If it is true, success. False. K will become k equal to 1. Check for k less than limit. If it is true, wait TB seconds. If it is false, abort. And then repeat the process. Next, we'll see about contention window. Contention window. Contention window. So the contention window is an amount of time divided into slots. When a station is ready to send, chooses a random number of slots. According to the binary exponential backoff strategy, the number of slots in the window changes, which means that it is set to one slot the first time and then doubles each time the station cannot detect an idle channel after the IFS time, which is very similar to the p persistent method, except that a random outcome defines similar to the which is very similar to the p persistent method, except that a random outcome defines the number of slots taken by the waiting station. Station needs to sense the channel after each time slot is an interesting point about contention window. However, if the station finds the channel busy, the process is not restarted. Just stops the timer and restarts it when the channel is sensed as idle. This gives priority to the station with the longest waiting time. Then next we'll see about acknowledgement. This is a contention window. Contention window, you can see in this busy, here is contention window. In between busy and contention window, you can see here IFS, and the size of this is binary exponential. This is found idle, continuously sense. Okay, next we'll see acknowledgement. With all the precautions, there still may be a collision resulting in destroyed data. In addition, the data may be corrupted during the transmission. Positive acknowledgement and the timeout timer can help guarantee that the receiver has received the frame. Next, we'll see about frame exchange timeline. Frame exchange timeline. Okay, frame exchange timeline. There is a figure that shows the exchange of data and controls in time. We'll see it later. The first point is before sending a frame, source station senses the medium by checking the energy level at the carrier frequency. Then in this there are 2 bits. The channel uses a persistent strategy with back off initial until the channel is idle. B point is after the station is found to be idle, the station waits for a period of time called DCF, interframe phase, DIFS. Then the station sends a control frame called the request to send RTS. The second point is after receiving the RTS and waiting for a period of time called short interframe space SIFS, the destination station sends a control frame called clear to send CTS to the source station. This control frame indicates that the destination station is ready to receive data. Then next we'll see about the third point. Third point, the source station sends data after waiting an amount of time equal to SIFS. The fourth one is the destination station after waiting an amount of time equal to SIFS sends an acknowledgement to show that the frame has been received. Acknowledgement is needed in this protocol because the station does not have any means to check for the successful arrival of its data at the destination. So, on the other hand, the lack of collision in CSMS/CD is a kind of indication to the source that data have arrived. Next, we'll see about network allocation vector. This is the diagram that is showing CSMA slash C and NAV. CSMS C and slash NAV. So here we can see NAV. Here we can see NAV. Here we can see SIFS. Here we can see SIFS. This is request to send, clear to send, CTS. Here is acknowledgement. Here is data. This duration is SIFS. This is DIFS. Okay, DIFS. And the source is A, destination is B, all other stations C and D. Okay, this is NAV. Now we will see about NAV, network allocation vector. question is, how do other stations differ sending their data if one station acquires XSS? So, in other words, what is this question saying is that how is a collision avoidance aspect of this protocol accomplished? The key is a feature called NAV. NAV. When a station sends an RTS frame, it includes the duration of time that it needs to occupy the channel. The stations that are affected by this transmission create a timer called a network allocation vector NAV. This NAV shows how much time must pass before these stations are allowed to check the channel for idleness. Then every time a station assesses the system and sends an RTS frame, other stations start their NAV. So it is said that before sensing the physical medium, each station must see if it is ideal, the physical medium. First checks its NAV to see if it has expired. So you see, this is a diagram that is showing the idea of NAV. Okay. Next we'll discuss about collusion during handshaking. Collusion during handshaking. The question is, what happens if there is a collusion during the time when RTS or CTS control frames are in transition, often called the handshaking period? Then two or more stations may try to send RTS frames at the same time. These control frames may collide. However, as there is no mechanism for collision detection, the sender assumes there has been a collision if it has not received a CTS frame from the receiver. Then the backup strategy is employed and the sender tries again. Next, we'll discuss about hidden station problem. Hidden station problem. Whatever is a hidden station problem, the solution to that is to make use of the handshake frames RTS and CTS. So in the previous figure we have seen RTS message from B reaches A. RTS message from B reaches A but not C. Then, however, as both B and C are within the range of A, the CTS message, which contains the duration of data transmission from B to A, reaches C. Station C knows that some hidden station is using the channel and refrains from transmitting until that duration is over. So next we'll discuss about CS, MA/CA and wireless networks. So whatever is CS, MA/CA, it is mostly intended for use in wireless networks. So whatever is a procedure that has been specified, it is not sophisticated enough to handle some particular issues that are related to wireless networks such as hidden terminals or exposed terminals. Then so those issues are solved by augmenting the above protocol with handshaking features. Next we'll go for controlled access. In the controlled access, the stations consult one another to find which station has a right to send. A station cannot send unless it has been authorized by other stations. Then there are three controlled access methods that will be discussed. First is reservation. In this reservation method, a station has to make or needs to make a reservation before sending data. Then whatever is the time, it is divided into intervals. Then in each interval, a reservation frame precedes the data frame sent in that interval. If there are n stations in a system, then there are exactly n reservation mini slots. Mini slots, n reservation mini slots, n reservation mini mini slots in the reservation frame. Each mini slot belongs to a station. When a station needs to send a data frame, it makes a reservation in its own mini slot. The stations that have made reservation can send their data frames after the reservation frame. So this is a figure that is showing a situation with 5 stations. You can see labeled 1, 2, 3, 4, 5. 5 stations and 5 mini slot reservation frame. You can see reservation frame, 5 mini slot reservation frame. Then you can see in the earlier one, the reservation, all mini slots are 0, 0. Here all mini slots are 0, 0 for those stations. Okay. Then in the first interval, only station 1, 3 and 4 have made reservations. Okay. In the first slot, only stations 1, 3, 4 have made reservation. So you can see data station 1, data station 4, data station 3. Okay. Made. In the second interval, only station 1 has made a reservation. Only station 1 has made a reservation. So you can see in this one, in this 1, 3, 4 have made reservation. So 1, 3, 4 mini slots are with 1. Whereas in 1, 3, 4, in this next second interval, only station 1 has made reservation. So that mini slot is occupied with 1 and only one station has made a reservation. Next we'll discuss about polling. So whatever is a polling that works with topologies in which one device is designated as a primary station and other devices are secondary stations. So all data exchanges must be made through the primary device even when the ultimate destination is a secondary device. The primary device controls the link. The secondary device follows its instruction. So it is left to the primary device to determine which device is allowed to use a channel at a given time. Then, so it is said that the initiator of a station is always the primary device. So whatever is this polling method uses poll and select functions to prevent collisions. The drawback of this is that if primary station fails, the system goes down. We'll see about select. This is a function. The select is a function. The select function, when it is used, is when the primary device has something to send. When the primary device has something to send, there is one thing to remember, that the primary controls the link. If the primary is neither sending nor receiving data, it knows that link is available. But the primary device sends it if it has something to send. Then when the however, is whether the target device is compared to receive, what it does not know, however. Then the primary must alert the secondary to the upcoming transmission and wait for an acknowledgement of the secondary's ready status. Then the primary creates and transmits a select SCL frame, one field of which includes the address of the intended secondary before sending data. Next is poll. Okay, this is also a function. Poll and this is used by the primary device to solicit transmission from the secondary device. So when the primary is ready to receive data, then it must poll each device in turn if it has anything to send. When the first secondary is approached, then it responds either with a NAK frame if it has nothing to send, or with data if it does. But if the response is negative, which is NAK frame, then the primary pulls the next secondary in the same manner until it finds one with data to send. When the response is positive, that is a data frame, the primary reads the frame and returns an acknowledgement ACK frame verifying its receipt. So this is the diagram that is showing the polling, select and poll functions in poll assess method. So select, here is poll. It will poll each device, okay, in turn. If it has to see here, first it will ask here this device whether it has to send. Next it will ask this device whether it has sent. Next it continues. Okay. If the primary device has something to send, then it is select function. Select, okay. So when the primary has something, then it is device something, the select function is used in case of select. Next we'll discuss about token passing. So this is a method. In this token passing method, the stations in a network are organized in a logical ring. So for each station, in other words, there is a predecessor and a successor. The predecessor is the station which is logically before the station in the ring. The successor is a station which is after the station in the ring. Then the current station is the one that is assessing the channel now. The right to this SS has been passed from the predecessor to the current station. The right will be passed to the successor when the current station has no more data to send. But the question is, how is the right to assess the channel passed from one station to another? Then, so in this method, there is a special packet, so-called token, that keeps on circulating through the ring. Then whichever station wants to have access to the channel and sends its data, there will be possession of that token to that station. So it is said that the possession of the token gives the station the right to access the channel and send its data. When a station has some data to send, it waits until it receives a token from its predecessor. It then holds the token and sends it data. So when the station has no more data to send, it releases the token, passing it to the next logical station in the ring. The station cannot send data until it receives a token again in the next round. So when the station receives a token and has no data to send, it just passes the data to the next station in this process. So whatever is a token management, it is needed for this SS method. But this one limitation is that the stations must be limited in time they can have possession of the token. The token must be monitored to ensure it has not been lost or destroyed. For example, if a station that is holding the token fails, the token will disappear from the network. For example, if a station that is holding the token fails, the token will disappear from the network. Then there is one more function of token management. What is that is to assign priorities to the station and to the types of data being transmitted. Token management is needed to make low priority stations release a token to high priority stations is final. Next we'll discuss about logical ring. So whatever is a token passing network, the stations do not have to be physically connected in a ring. The ring can be logical one. So you can see there are four different physical topologies that can create a logical ring. So first one you can see physical ring, next one is dual ring, next is bus ring, next is star ring. Okay, we'll discuss one more. In the physical ring topology, when a station sends a token to its successor, the token cannot be seen by other stations. The successor is the next one in line. So this means that token does not have to address of the next successor. What it means is that the token does not have to have the address of the next successor. But there is one problem that may occur is that with this topology, if one of the links the medium between two adjacent certain fails, the whole system fails. Next we'll say about dual ring topology. In this, it uses a secondary so-called auxiliary ring which operates in the reverse direction compared with the main ring. The second ring is for emergencies only. If one of the links in the main ring fails, the system automatically combines the two rings to form a temporary ring. After the failed link is restored, the auxiliary ring becomes idle again. So, each station needs to have two transmitter ports and two receiver ports for this topology to work. Whatever is the FDDI, fiber distributed data interface, and CDDI, copper distributed data interface, use this topology, which is a high speed token ring network, so called FDDI and CDDI. Next, we'll say about bus ring topology, which is also called a token bus. Here, the stations are connected to a single cable, so called a bus. But those, however, will make a logical ring as each station knows the address of its successor and also predecessor for token management purpose. Then, when a station has finished sending its data, it releases a token and inserts the address of its successor in the token. Only the station with the address matching the destination address of the token gets the token to access the shared media. The token bus LAN standardized by IEEE uses this topology. Next, the last one is a star ring topology. The physical topology is a star. In this case, there is a hub which acts as a connector. So, whatever is a wiring inside the hub, it makes the ring. The stations are connected to this ring through the two wire connections. So this topology makes the network less prone to failure because if a link goes down, it will be bypassed by the hub and the rest of the stations can operate. So adding and removing stations from the ring is easier, but this topology is still used in token ring LAN. So with this I have completed the review of module 2. I request all of you to go through this and read it and write the assignment. I'll stop here.